All right, guys. So this next section of our notes covers both topic 8.3 and 8.4. It's all about population ecology. So if you remember the big diagram that we talked about at the beginning of this unit, the population level of ecology is all about individuals in the same area that are of the same species. So there's a lot of successful interbreeding occurring. And so population ecology is really about the growth of populations. We talk about birth rates and death rates and factors that affect those. So we're going to jump right into what impacts the size of a population. And so you're looking for the section of your notes that has this diagram right here, and I'll come back to that in just a second. There are four big things that impact whether a population is going to get bigger or smaller. The first thing has to do with births. So a birth rate is going to impact population size. And when you think about birth rates and kind of predicting if the birth rate is going to be high or if the birth rate is going to be low, you're looking at demographics of the population. You're looking at how many individuals in the population are female and how old are those females? Are they of reproductive age or are they older? You would also look at things within the population that exist or don't exist, things like healthcare. And so if you have a good healthcare structure in a country, then you're going to see that the majority of your births, and I'm talking about humans, the majority of your births are going to be successful. Those babies are going to live. If you don't have great healthcare, either maternal healthcare for the mom while she's growing the baby, or when the baby is born, if there's any issues, then you're going to find countries that have a higher infant mortality rate. So when we think about birth rates, you can look at the breakdown of a population and you can start to infer that population is going to have a high birth rate because there are a lot of reproductively active females in the population. Or, you know what, that population is going to have a really low birth rate, probably because they have lack of health care and the females are possibly older and not reproducing. We look at death rates as well. So death rates, again, the same things can be said. You can look at things within the history of a population or country in this case that can predict death rate or influences on death rate. So again, healthcare availability. If people are getting sick, do they have access to healthcare? Is that healthcare good? If not, you might have a higher death rate in that population. Has the population experienced anything like war or famine or a plague, which is why this graph is in your notes? Does the population have access to resources, whether that is food or water? For us, I put economic resources. Are there high rates of unemployment, or can people access jobs and thus a living wage to be able to purchase resources that are essential for health and for life? So this population graph in your notes shows, now it goes back a long time, and there's even a break in that timeline right here to kind of shorten the span of the x-axis. But if you look at, there's a dip right here. That dip indicates a decline in the population, which was the bubonic plague. And then you can see a pretty sharp increase here in growth around the year 2000. Now, that's number of individuals in the population. There are other things besides individuals being born into or exiting by death that impact the size of a population. So let's talk about immigration with an I and immigration with an E. I know they sound really similar, and so if you need to exaggerate that, immigration, to help distinguish them, great. Now, the issue with the last two things that are going to impact population growth is that they're really hard to get accurate data on. So most population growth rates are calculated by births and deaths. That is easier data to access. So immigration is individuals that are entering a population. Immigration are individuals that are leaving a population. for some reason or another. So when this spikes, it doesn't necessarily mean that we started rapidly mass producing, although our birth rate did go up. This is a human population for the world. This also includes individuals that are coming into and out of a population. Look down here at the US. So you can see from 1919 to 2019, we've kind of fluxed up and down and up and down. And we're currently in a slight downtrend for population growth rate. So this is a percent change of the population, which is a little more relatable to an overall growth rate. So we are in a decline. Does that mean that the US population is shrinking? Not necessarily, but it is less than it was in the 40s and 50s. And so we can track that back to some historical events, right? We'll talk about this a little bit more in class, but there are moments in history that you can see documented in the growth of our population. When it comes to population ecology, this is still section A of your notes. There's a little bit of math that you have to know about calculating birth rates and death rates. And the good news is the math is very simple math: multiplication, division, addition, and subtraction. You're going to be fine on the math. The important thing is to know what the math indicates. And so in this next section, or in this same section of notes, I want you to write out some formulas using words so we know exactly what they mean. If you're asked to calculate a population density, that literally is the number of individuals divided by the area in which they live. And that is density as a calculation in general. So if you're asked within a question set about the population density, number of individuals divided by the area that the question or the prompt provides you. A birth rate, which is written as B, is the number of births out of the entire or total population. So number of births divided by total population. Death rate is the same. That value is D, is the number of deaths divided by the total population. And once you have those two, you can calculate a population growth rate. So once you have a birth rate and a death rate, you take your birth rate and subtract out your death rate, and that gives you the overall growth rate of the entire population. If you calculate this value and it is a negative number, that means that your population growth rate is negative, which means that the population is in decline. But if you calculate this growth rate and it's a positive value, it means that your population is growing. Another calculation that you could be asked is a survivorship rate. And so that is the number of individuals or organisms that survived out of the total population. So I'm going to give you a practice here in the blue box, and you can pause the video and try it, and then unpause the video and the answers will appear in the red box. Please, please, please do this. Your quick check tomorrow in class or Monday in class will involve some math calculations. So give these a shot really quickly here as we kind of go through the PowerPoint. So in a population of 1,000 beetles, 25 die on a particular day while 10 were born. So calculate a death rate for that day, calculate a birth rate for the day, and then give me an overall population growth rate for the day. So pause the video and calculate based off of 1,000 beetles. If 25 die, what's the death rate? If 10 are born, what's the birth rate? And then give me a growth rate. Unpause the video when you're ready. Here are the answers. 25 out of 1,000, your death rate is 0.025 for the day. Here is your birth rate for the day. And your population growth rate is actually a negative value because more are dying than are being born. All right, moving on into the next section of notes, let's talk about how fast populations can grow. There are two models for population growth: exponential and logistic. So the first model that you have in your notes is exponential, and you see this diagram right here. So over a period of time, what is the number of individuals in this population? These are often referred to as J curve, because looks like a J curve population growth rates. This is growth that can happen without limits, typically because there's an abundance of resources, food, water, also space is included here. And so really populations can kind of grow and grow and grow and grow and grow as much and as quickly as they desire. It's very, very rapid growth, which is where the exponential comes in. Bacteria are a great example of organisms that experience exponential growth. Some weeds are great examples of those that experience exponential growth. Right now, if you go outside, you could probably see tons and tons and tons of those dandelions that blow in the wind, the like white little puff balls, they blow in the wind. You could have one on one day and you come back the next and you have an entire field of those weeds. They have experienced as a population exponential growth. There's a little bit of math with calculating exponential growth. So exponential growth is going to be the calculation of something called Rmax times N. Now let me define Rmax and N. Rmax is another way of writing your population growth rate, what we just calculated a second ago. Population growth rate can be written out growth rate. It can be this variable right here, Rmax, or it could be this variable right here, dn over dt. And we'll see some problem sets tomorrow in class that use all of those. They all mean the same thing. Rmax, growth rate, dn over dt, they all mean the same thing, which is a population growth rate, which we just calculated and saw a second ago, birth rate minus death rate. N in this formula is the number of individuals in the population. So you basically take your growth rate times the number in your population. And typically, exponential growth problems have you track the population size over multiple generations or over long periods of time. So here's an example for you. If a population of 100 individuals have a growth rate of 0.25, now remember this word right here could have been taken out and I could have dropped in this variable Rmax, has an Rmax of 0.25. I could have also dropped in this variable right here, has a dn over dt of 0.25. They all mean the same thing. How large will the population be in 3 generations? So here's what you have to consider. You're going to figure out, based on the growth rate, how many individuals are added to the population each generation. And you just have to kind of keep track of that. So generation 1, we have our initial 100 individuals times our growth rate. That means we're going to add 25 individuals to the population within generation 1. So when I move forward into generation 2, I need a new starting population size. I need 125 as my start because in generation 1, I added 25 to the original 100. So see how this builds one on top of the next on top of the next, which gives us our increase of exponential growth. So generation 2, I've got 125 to start with. That's what happened after generation 1 individuals were added. And then I apply the same growth rate, 0.25. That tells me I'm going to add 31.25 to start the next generation. And so generation 3 starts with 156.25 times my population growth rate. I've added 39.6 individuals to the generation. And so after 3 generations, I'm up to 195.06 individuals. That is exponential growth. If it were like a steady growth, nobody was the growth rate never changed, but also we never included, that means that our birth rate either went up, maybe our death rate never came down. for whatever reason, it wasn't a steady 25 individuals added to the population every single generation. That number would have gotten us 175. Instead, with the exponential growth model, because you're adding those individuals to the population before you do your next generation's value, the number after 3 generations ends up being 195 and not 175. So again, not challenging math, just keep in mind what you're actually calculating here. The second growth rate is called logistic growth rate. Logistic growth rate is this diagram in your notes. Logistic growth rate is an S-shaped curve. And really, logistic growth rate is exponential growth up to a certain point. And this line here is given a variable called K. So exponential growth until some kind of a limit or limits are reached. Those limits indicated on your graph as K, those are something that is something called carrying capacity. And we're going to talk about that a little bit later in our notes. But for right now, let's just know that carrying capacity is essentially limits to growth that exist. And it is denoted with the value of K. In your notes, once K reaches that growth plateaus, in real life, this is actually what it looks like. So once K is reached, there's something called dynamic equilibrium, which means it doesn't plateau. It sort of goes above carrying capacity. And because of the limits, individuals die. And so it dips below carrying capacity. That leaves a little more resource availability. It climbs above carrying capacity again. And it just sort of goes up and down and up and down and wavers here. That's a little more realistic of life. It doesn't fully plateau. The math here in logistic growth is basically what you calculated for exponential growth. So that is a growth rate. It was your population growth rate times individuals in the population. That goes here in the formula, times this value called K minus N divided by K. So N is always the number of individuals in the population, and K represents the carrying capacity of that population. Excuse me, the limits that exist to population growth. Here's what you should notice. As your K and N values numerically, as these numbers get closer and closer and closer to each other. So as your population number N approaches K, your carrying capacity, this calculation as a value, if you plug it into your calculator, gets smaller and smaller and smaller and smaller and smaller, which indicates that the population is growing at a slower rate and eventually will grow at a negative rate, which is what brings our population back down below carrying capacity. And so we'll do some practice in class with this. But logistic growth is a little more realistic of populations because limits really do exist. Goodness, I have something in my throat. This last bullet just popped up here indicates a slowing population growth rate as N approaches K. All right, let's talk about this diagram in your notes. These are called survivorship curves. Survivorship curves essentially talk about at what point in your life are you living? Do you have a really high rate of life? And at what point in your life are you dying? And so survivorship curves, there's 3 types of curves. They are based on your reproductive strategy and also your life strategy. And I'll kind of explain what that means. Let's look at a type 1 curve because type 1 curves are humans. And so that might make a little more sense to us. So the graph here, number of survivors within the population. Goodness. And at what age you are surviving. So look at the type 1 curves. When you are young, most of us are surviving. As you get older, we start to die. So in a type 1 curve, we have a higher rate of mortality, that's death, in later life, and a high survivorship in early life. That is because as humans, we have something called a K reproductive strategy. K reproductive strategists choose to have fewer offspring in life. And that means that each individual offspring is larger and typically healthier. And you can think about what happens anytime we in the human population see the birth of multiples, twins, triplets. Those babies individually are smaller and smaller because there's really only so much space that mom can incubate them in her uterus before they come out. They're born earlier in life typically. So the fewer offspring you have, the larger each offspring would be, and thus potentially healthier. We also choose to raise or care for our offspring, which increases an infant's chance of success, survivorship. And we choose to reproduce later in life, which means we typically have the resources available to us to care for our offspring. So type 1 survivorship curves show a really high survivorship early in life. And then as we age, we start to die. Type 2 survivorships in the middle of the graph, there's not that much to say about type 2 survivorships, except there's a constant mortality rate throughout life, regardless of age. So age doesn't really seem to play a factor on whether you survive or die. These are individuals that typically have a shorter lifespan, birds, lizards, rodents, and there's not really a reproductive strategy that is associated with type 2 survivorship curves. Type 3 survivorship curves are the opposite of humans. We actually see a really high rate of mortality in early life. But if you survive, you can actually live for a really long time. Sea turtles are a great example of this. Turtles lay a clutch of eggs, upwards of 300 eggs. A very small portion of those turtles actually make it into adulthood. But if they do, they can live to be 100 years old. This should say type 3. That's a typo right there. Type 3 survivorship curves are individuals that show an R reproductive strategy. Gosh, these individuals reproduce early in life and they have a ton of offspring, and those offspring are really, really small. They also don't stick around to care for their offspring either. Two things that I want to point out. You don't have to write them down if you can kind of reason through them. The first thing is the number of offspring that you are producing is always a trade-off to size. That means the fewer offspring that you have, the larger each will be and potentially healthier and have a higher chance of survivorship. If you are mass producing offspring, they're going to be really small and could potentially die because of that. The second thing is that the age of the parents, like when you actually have offspring, is a trade-off to resources and energy availability. If you reproduce really, really young, you probably have tons of energy to care for your offspring, but typically those that reproduce so young don't implement that kind of reproductive strategy. And so, because you're reproducing so young, most of these organisms choose to leave their offspring, and their offspring then don't have great access to resources. If you're reproducing really, really old or later in life, you might have great access to resources for your offspring, but your physical energy availability to care for them is going to decline. Last thing to talk about here, and then we'll wrap it up, are these diagrams. So this last section in your notes, these are population pyramids. If you are in AP Human, you've probably seen these and talked about these. We're not going to go into that much detail for AP Bio. So population pyramids essentially show a country. These are created for countries, and they show the demographics of a country specific to age of individuals in the population and the sex of the individuals in the population. So you can look at, there's usually a line coming down the middle. On one side are going to be males in the population, on the other side are females in the population. This one's color coded. So everything that is blue, those are individuals that are 0 to 14 years old. Everything that is yellow, 15 to 44, and the red are the older people in the population. Sometimes there is an an axis over here that tells us that data if the diagram isn't colored. So you could say these are all of the males that are 0 to 14 years old. These are all of the males that are 15 to 44, and these are all of the males that are 45 to 85. So you can essentially, because you're looking at age and reproduction comes with age, and you're looking at males and females, you can start to talk about population growths. So there are 4 different models here that can be represented. The first model is a rapid growth model. So you see that right here under the diagram. Rapid growth countries, they are experiencing, just as it sounds, rapid population growth. The country typically will have many young children that are of reproductive age, but very few older people. Now, that could say a couple of things. That could speak to the healthcare that exists within the country, or access to healthcare. It speaks to a lifespan, a shorter lifespan, either because of resource availability or something like war or famine. It also speaks to education. So if you have fewer older people in the population, who is actually taking care of the kids? You have kids taking care of kids. And so this can sometimes indicate countries that are economically challenged. They're typically more impoverished countries where kids are dropping out of school to work to provide income for their families, because those in the population that would typically provide, the older people in the population, they're gone. And so we see lower education rates as a result, and the cycle of poverty can often continue. Kenya is a great example of a country that is experiencing rapid growth. The next model that you see is a slow growth, and that's us. So this is a more stable growth rate. You have older people that are capable of working, caring for younger people that are now available for school. So education rates are higher. You typically have better healthcare in populations that have slower growth, which means there's a lower mortality rate, or you could say a higher life expectancy, which is lifespan being longer. These are typically more economically developed countries, ours being one of them. If we move to the third diagram, this is a 0 growth population. So when birth rates and death rates are relatively the same. So the base of the pyramid is going to be it looks really similar to slow growth, but the base of the pyramid is smaller than slow growth. There are a couple of countries that are experiencing 0 population growth. Italy is one of those. There's lots of reasons. And so I'll just speak to some of the things that are going on in Italy right now. There's lots of reasons that a country could be experiencing 0 population growth. So Italy is an older population. The economy is slower. And so parents look at you have really high rates of education people in Italy, and so parents are essentially making educated decisions to have fewer children because they're really expensive to take care of, and Italy's economy is not what it used to be. So the choice to have 1 or 2 kids versus 5 or 6 is really what we're seeing here with the 0 population growth. I know that probably 15 years ago, I think they also cited that more individuals were focusing on their career. And so they were waiting until later life to do things like get married and have children. And so as a result, starting later, essentially, they had fewer kids as well. The last model is a negative growth population. So we see death rates that are higher than birth rates. And really, what we're looking at here, you can see a couple: Germany, Bulgaria, Hungary. There can be lots of reasons for negative growth rates in the population. Birth rates, so I could speak to Germany specifically. Birth rates are relatively low because of sort of the state of the country and what has happened historically, culturally. People aren't necessarily wanting to bring kids into that existence, that into their world. So we're seeing a negative growth rate occurring in Germany. Okay, the remaining bits of our notes we'll cover in class, but make sure that you have these taken. When you're done, you are done.